Last video we talked about how to derive the mass flow rate of this plane, and then I will assume that you know how to derive this plane also. Is the same exact formula, same exact derivation. And then now in this video we'll try to combine these two equations, okay, this one and this one, with some other things, and eventually you can find something. Okay, so as you can see, the left hand side of the equation 1 is QR minus QL. So in fact we are trying to take this equation, okay, this equation minus this equation, okay, so we are trying to do that, okay. So as you can, if you were to compare, okay, this is simply the same. Maybe I should bring all this dude over here. You double check. I'm not lying you. This portion is QR and this portion is QL. They are the same thing. Okay. So if you take QR minus QL, you will eventually get this over here. So we shall do it. So if you were to take this minus away, so this thing is QL, right? So minus multiply this whole thing is actually plus. Okay, so what I mean, maybe I should sort everything out first. So this is this, and this is this. So I hope you understand how I derived that. So this thing, so this is this, right? So this is QR and this is QL. I think I just do until here, right? Because someone called me earlier. So QR is equals to this thing, and then QZ is equals to QL is equals to this thing. So if you open out this bracket, this one will be minus, right? Minus and minus multiplied by minus, you have plus. So eventually you have this dude over here, right? And then so since this one minus this one, will cancel out. And hold on the fan. Yeah. So finish the phone already, and then so plus, so you know this minus this, so plus this one plus this one. Okay, so this thing plus this one. Okay, well this thing cancel away. Okay, they cancel each other. So you will have what do you have? Okay, what do you have? So hold on, why you have this over here, right? So what's the difference? So it's this thing u del p over del x plus. Okay, so maybe I should take down this portion over here. Okay, half plus half, you have this portion over here, right? Half of this plus half of this, you only have this piece over here, right? So let's go back. Textbook. So we have this thing. Yeah. So we are the same. So therefore, this is this, and then now dx dy dz, you make everything in terms of, because they're volume, right? X times y times z, you have a volume. And then let me check it out for this. Okay, to explain this is a little tricky. Okay, to explain how do I derive from this big piece into this one. Okay, so what I thought was is actually to open up the thing. So eventually, because as you can see, del x, they are all constants. So I just remove them. Okay, so that you're not confused anything. Okay, what I mean is that eventually the x will still stay, but only this numerator stays the same. I mean, then only the numerator changes. Okay, as you can see, the numerator are different. Okay, while the denominator, the x is the same. So let me take a look. Okay, so u del rho. Okay, u multiplied by del rho plus del, sorry, not del, but rather than density times del u is equals to over here. Okay, so nonetheless, if you want to include, I'll just include the del x also, fine. Okay, instead of any, make sure there's no confusion. Okay, so if you can see, if I were to multiply it in, okay, so let's sub in some values for del rho in order for you to understand what is actually going on. So imagine, as you know, del rho, this del is stating that it's a very small value of density, right? Small amount of density. So maybe I should take it as 0.01. Okay, in this case I take it as 0.01 for example. So as you can see, this u multiplied by this is del. Okay, this is 0.01 is del. So plus density times 0.01 u over del x, and if you were to expand it out, you will eventually get this one over here, right? So when you multiply 0.01 rho times u, you have this, and when you multiply 0.01 u times density, you have this. Okay, so if you were to multiply, so if you were to so as you can see, this is a small change of del plus a small change of del. Del is just some values. Okay, so you have, in other words, you have 2 del u rho del x. So what does this mean? 2 del is because 0.01 is just some values of del, right? Just plot in any small number will do. So in this case, actually, this 2 del is actually del also, because del is a very infinitely small number. So in this case, you see, so this is why we have del u rho del x. Okay, so if you were to open up, so in other words, I don't know whether you understand. So in other words, if let's say you were to continue to sum it, 0.01 rho u plus this, you have 0.02 rho u, right? So this 0.02 is just some small values. You can call it del also. So this is why del rho u over del x. So this is where we get this portion over here. I mean this portion over here. So allow me to explain it again. So I take this portion over here. Okay, I rewrite over here. Okay, I didn't change anything. And then I just simply sub in this small portion of rho. Okay, this small portion of rho, I say that it is 0.01 rho. Okay, and then same to this one. I'll just say that it is 0.01 u. Okay, velocity. So when I multiply in and I expand everything, okay, and then you sum it out, you eventually get 0.02 rho u, right? Although as you can see, this 0.02 is actually the summing of some values of del. In this case, at first you remember we sub del rho as 0.01 rho. So this del is just some infinitely small number. So similarly, 0.02 is also some infinitely small number. So we can just say that it is del. So del rho u over del x is being derived over here like this. Then the x dy dz is derived in this form. So I hope I didn't confuse you, and I think that it's pretty good. And then wow. So far we have talked about the x-axis. Okay, at first we talked about the velocity u going into this thing, right? And then y and z did not change, right? Only the only x plus dx over 2 and x minus dx over 2. So everything what I'm talking about is actually in terms of dx. Okay, so this we are talking about one dimensional now. I mean x direction. Then throughout we derive all these things. Okay, we take the mass flow rate of r on the right side minus the mass flow rate of the left side, and eventually we will get this equation over here, and this is the eventual mass flow rate of the x direction. And then as you can see, this is x direction, so we can say that the mass flow rate across the x direction is equals to this, while the y direction is equals to this, and z direction is equals to this, while u indicates the velocity in the x direction, v indicates the velocity at the y direction, and w as the z direction as per shown in this portion. So u, v, and w, x, y, and z. Here I didn't cheat our feelings. So after you get this, okay, the total mass flow in the left hand side of equation 1. So the equation 1 is actually this equation. So the total mass, it can be rewritten as this, okay, qx. So you sum it up all this qx, qy, and qz, and then you write it in terms of this. So this equals to this, and then this plus this plus. So this plus this plus this. Okay. So this is just this is this, this is this, and this is this. Okay. So and then you just sum it up, you do some factorization, you factorize out the dv, you get this portion over here. And this portion simply describes the total mass flow rate. Okay, so mass flow out minus mass flow in. Okay, so this portion over here describes. So this portion over here describes this relationship. And then for the right hand side of the equation, which is this one, the net change of mass flow inside the volume. So the net change within this volume itself is taken by this equation over here. It is some small amount of mass over a small amount of time. Okay, and then as you can see how on so the mass itself, as you remember, density is equals to mass over volume. So mass is just density times volume. Okay. So therefore you can rewrite this small mass equals to small density times volume, right? And then this volume is in terms of a very small change of volume, because there's different changes in the volume itself, therefore it's dv. So you ask me, is there any change in volume? Yes, because as you can see, you have this box over here. Across time, you may have different volume, different mass. Okay, across time, the amount of mass is different. The amount of volume you're looking at is different also. Maybe at time, this is time equals to 5, you are looking at this volume, right? So maybe at time equals to 3, at time equals to 3, you're looking at this volume over here is slightly bigger. So there's a change of volume itself. So I'll leave you to think about it. Nonetheless, this is how we derive the equation for this portion over here. Okay, for this portion over here. And then so this is the right hand side of the equation, of this long piece of the equation. Since we have the left and we have the right, why not we sum it up together? So you have, this is the left hand side one. Okay, so let's put it over here, and then this is the right hand side, we just put it over here. And then because due to the conservation of energy, okay, mass conservation principle, everything has there will be no change in the system unless you input any changes. So therefore you can just straight away bring this over here. So okay, you can clear away the dv first, because the dv is the constant between these two equations. Therefore you have this equation over here, then you just bring this thing over here, and you have tada, equals to 0. So what is this meaning? Okay, so I mean what is this mean? Okay, what is the SI unit? The SI unit itself by odd is actually meter per second square acceleration. So it's a little weird how we actually derive mass flow, density, volume, suddenly you have a acceleration out. Okay, so what I have in my previous thing is this. Okay, so let me explain. So how do we eventually get the acceleration is that you have this thing that we are looking at, this box. Now we are looking at the side view. Okay, you have a velocity in, okay, and then we have velocity out. So we're talking about velocity. Okay, meter per second. Okay. Nonetheless, you can also, let's just take it as meter per second. So meter per second out. So this is V out. V out is over here minus V in. So you'll still get the change in velocity, which is meter per second, right? Everything is the same SI unit. And then, however, the V in at this point is time 0 sec, while the V out maybe is 5 seconds. So V out minus V in, there is a certain change in time, which is 5 seconds, right? So del V over del T, you have velocity over time is equals to A. So eventually, what you're actually measuring is actually measuring the change in the velocity itself. Okay, the change in the velocity itself. And then, because typically you're talking about change in the mass flow rate, okay, kg over kg per second. So, because you have actually changed the mass, as you can see, there is a transition point where you actually change the mass into volume. Okay, you're actually trying to see things in terms of volume and in terms of the change in volume. So typically you're talking about, when you're talking about volume, you're talking about the x, the y, and the dz, right? So we are talking about these things. And therefore, this is why we often use the meter per second, in this case, the velocity. So maybe it's the x. So now I think it will be much clearer. So this line is actually dx per second minus dx per second. So in other words, this is just meter per second, that's all. So eventually, the change in the volume across time, you get acceleration. So this is what the whole system is actually trying to derive. More all in all, it's a little complicated. As you can see, you have del t, you have del x, del y, del z. So the del t itself is a change in the whole system. Okay, it's a change from this point to this point, while del x, del y, del z is the change in the configuration of the volume itself within the volume. Okay, within the, as you can see, this is rho times u. Okay, so this is, so actually this whole thing is talking about the volume within the volume wise, the changes in the volume itself. Okay, although it may be very abstract, but yeah. Nonetheless, if you were to take del v, okay, the change in the velocity divided by change in time, times change in time, you'll get the meter, which is perhaps in other words dx. Okay, you'll get the amount of, so because the y dz is already been taken care of, so the x is just a gauge itself telling you that how much of this stuff is within here. Okay, how much is within here. Okay, so across certain time, maybe at 3 seconds, maybe at 3 seconds is over here, right? So if you multiply at 3 seconds, you're telling somebody that, okay, you have some value of dx. Okay, this is another dx. Okay, so I hope I didn't confuse you anything, and I may actually help in some, like, telling you all these things. This is my perception, I may be wrong. So yeah, so I'll see you in the next video to talk about special case, and then the rest. So I'll see you in the next video.